Oh, good morning, good afternoon, good evening, good night, whichever is applicable to you. Welcome to chapter 10 of virtual lecture. Chapter 10 is on chemical bonding 1, the Lewis model. In chapter 11, we will look at two other models of chemical bonding, that is atomic theory and molecular orbital theory on chemical bonding. As usual, the chapter is split into three sections. There is part A, part B, and part C. Make sure you watch all the lecture recording. In part A, I would like just to start by defining, first of all, what a chemical bond is. A chemical bond is simply defined as strong electrostatic force of attraction between two or more atoms, or just strong electrostatic force of attraction between atoms. That's how we define a chemical bond. In chapter 10, we will look at the Lewis model of chemical bonding, Lewis chemical bonding. Why do atoms form chemical bond? Or bonding theories explain the bonding theories, either molecular orbital, valence valential orbital bonding theory explain why atoms are tied together to form molecules. Bonding theories also explains why some combination of atoms are stable and why others are not stable. For example, why water is stable and not hydronium. We can predict from the chemical bonding, also bonding theories, the shapes of the molecules. This is what we look at in chemical bonding too. We can also use bonding theories to predict the chemical and physical properties of compounds, uh, physical properties as well as chemical properties. In this chapter, we will look at the Lewis model. Lewis, you see here, he was an American chemist. We have discussed his name before. Lewis. It's the first scientist to propose that when atoms come together, they to form compounds, they make use of their valence electron. Lewis emphasized valence electron, and valence electrons are electrons in the outermost shell. So if I define that, remember valence electrons are electrons in the highest and value or the highest principal energy level. These are responsible for chemical bonding. In Lewis' model, valence electrons are represented as dots. For example, we'll see later on, group 1 will have one dot representing the valence electrons. Group 2 will have two dots. We'll look at it later on. You don't pair them up until they are singly distributed around the atom. We also call this electron dot symbol. This is what we look at later on in section 10.5. All right. So Lewis structures allow us to predict many properties of molecules, and that's why it's important for us to learn the Lewis model of chemical bonding. The fundamental question here is why do atoms bond or form chemical bond? Chemical bonds form because they lower the potential energy between the charged particles that compose them. Charged particles, these are the atom. The point here is that chemical bond or bonds are formed when potential energy of the bonded atoms is less than the potential energy of the separated atoms, right? Remember, to calculate this energy, you need to consider the interaction between nucleus to nucleus repulsion. What this means is we need to factor in this nucleus to nucleus. If we have, let's say this is an atom and this is another atom here. If this is the nucleus and this is the nucleus, this is the nucleus to nucleus, right? This is the nucleus to nucleus, electron repulsion. So if we have an electron here, remember they are negatively charged, so electron repulsion also affect the potential energy. And then the nucleus to electron. Remember, in the nucleus, we have the protons, and it will interact with electrons outside the nucleus in the neighboring atom. All these interaction, nucleus to nucleus, remember there is positive in the nucleus, nucleus to nucleus, electron to electron, and then protons in the nucleus for the neighboring atom, the electrons of the neighboring atom. All these determine the potential energy, which explain why atoms form is because they want to lower the potential energy. Cruising to 10.2, this is a section on the type of chemical bonds you need to commit to your memory. There are 3 types of bonds, which I know we have covered or we talked about it in the previous chapter. There is ionic bond, which is formed between a metal and a non-metal. So by now, when you are given a chemical compound such as NCl, this is a metal, all right, and this is non-metal. So the type of bond here is ionic. It involves transfer of electron. Generally, metals tend to lose their valence electron. For main group elements, it's easier to, or you should be able to determine the number of valence electrons. So sodium will lose 1 electron to chlorine, and this will form sodium, which is a cation, and then the chloride, which is the anion in case of sodium chloride. There's transfer of electron. For non-metal and non-metal, it form, this is ionic, 1 ionic bond. So here is the ionic bond, which is a strong electrostatic force of attraction between metal and non-metal. Positive repel, negative repel, but positive negative to attract to form ionic. Now, covalent bond is formed between 2 non-metals sharing their valence electrons so that they end up with A. So there is the sharing. E.g., we have hydrogen gas, they will share their electrons. So I have 1 hydrogen there. There is another hydrogen here. They share the electron to form a chemical bond. For most cases, you may also see that. And then lastly, metal to metal is metallic. It's just a cation in a sea of electrons. We will look at the end at the end of chapter 10, this type of bond. So you can study on your own, make your own notes of these three types of what? Three types of bond. Here is an example of the three types of bond: sodium chloride, ionic bonding, covalent bonding, sharing of electron, water molecule, and metallic bonding, just as ions in a sea of electrons. In a sea of electrons constitute what we call metallic bonding. So there are three types of bonding you need to learn. Ionic bonding between metal and a non-metal. Should be able to identify a metal or differentiate a metal from a non-metal on the periodic table. You'll be given the periodic table. So here, let's start off with ionic bond. Ionic bond is formed when an electron or electrons are transferred from a metal to a non-metal. So generally, metal loses electrons and then they become cation, positively charged. Remember the trend on ionization energy. Metal tend to lose their valence electron because they have very low ionization energy. Non-metal on the other side, okay, when a non-metal cane electron become an anion. Caning and losing has to do with what we call the octet rule, which we look at it later on. So remember, the type of bond which exists between a metal and a non-metal is ionic bond. A covalent bond is formed when two non-metals share electrons in such a way that they end up with 8 electrons. They end up with 8 electrons. So if we have, for example, H2O, with an exception of hydrogen, most covalent bonds end with 8. So in this case, oxygen, hydrogen, there is the sharing of electrons here. There is the sharing of electrons between oxygen this should be shared. So the shared electrons are right there. So the sharing of electron has to do with fulfilling what we call the electron or the octet rule. So when metal or non-metals bond together, it is better in terms of potential energy. So the potential energy is lowest when electrons are between the nuclear. These are the electrons between the nuclear and constitute what we call covalent bonds. So given the periodic table, you should be able to classify or identify the type of bond which exists in a given polyatomic ion or compound. Remember, ionic bond exists between a metal and a non-metal as a result of transfer of electrons, but covalent involves sharing of electrons. Lastly, the type of bond which I want you to learn is the metallic bond because of low ionization energy of metals. That means they lose electron easily. All right, energy of the metals allows them to lose electron, and in this case, valence electron. The simplest theory of metallic bond involves metal atoms releasing their valence electron to the shared pool of atoms or ions. And check on this, read more on metallic. Here is a conceptual question which I want you to make your own notes on. Ionic compounds ionic bond, covalent molecules, all right, and covalent bond. If I look at this question, the correct answer is C. Ionic bond exists between a metal and a non-metal. Carbon is a non-metal, hydrogen is a non-metal. So here we have covalent. Likewise for the dinitrogen monoxide, we have two non-metals, and this one, magnesium is a metal, fluorine is a non-metal. The type of bond which exists between metal and a non-metal is ionic bond. So the correct answer here is C, magnesium fluoride. All right, let's see, representing valence electrons with the dots. First of all, given the periodic table, you should be able to predict the valence electrons, group number for main group, all right? For 10.3 node, group what? Group number equals to number of valence electron, number of valence electrons. For group 1, they'll have 1 valence electrons. Group 2, they'll have 2 valence electrons, except for group 8. Helium is the only exception with 2 valence electrons, yet it's in group 8. So you know now, or you should be able to predict the number of valence electrons given the periodic table. In Lewis model, we represent the valence electrons using the dots. These dots represent electrons used in chemical bonding. Sometimes it can be shared or completely transferred from one atom to the other. These valence electrons are the most important in chemical bonding. So at the outset, as we move forward in chapter 10, remember Lewis model focuses on valence electron. And you know what valence electrons? Electron in the highest end value, all right, in the outermost shell, or for main group elements, you should be able to use the periodic table to predict the valence electrons. Here is part of the periodic table showing the valence electrons as well as the Lewis symbol. Remember, the dot represents the valence electron. All group 1 will have 1 dot with the chemical symbol for an element in question. So if you look at group 2A, remember these are the main group. The A's on the periodic table. Each element is represented with the dot which represents valence electrons. So here, all group 5 will have 5 dots, 6 will have 6 dots, and it's important to note that you don't pair them up until they are singly distributed. Watch this. For nitrogen, this is how you go about 1, 2, 3, 4, 5. So you have 5 valence electrons. For group 7, such as fluorine, 1, 2, 3, 4, 5, 6, 7, 8. Not 8, but 7. For fluorine, it should be 7. So 1, 2, 3, 4, 5, 6, 7. Should be 7 for fluorine. And the point here is you don't pair them up until they are singly distributed around the atom. Is when you start pairing them up. And remember, the dots represent the valence electron. For group 1, you'll see they have 1 dot. Group 2, they have 2 dots. You don't pair them up. For group 8, except helium, they will have 8 dots around them. This was proposed by Green. G stands for Green-Lewis. He was an American chemist who developed a method to denote potential bonding electrons by using 1 dot for every valence electron. So remember, the dot represents valence electron. Or you should be able to also use the periodic table to determine whether the atom will lose, gain, or share the electron. In losing, gaining, or sharing, this has to do with fulfilling or achieving the octet rule. Octet rule states that when an atom form a chemical bond, either they transfer or lose valence electron, they end up with 8, whatever the atom in question being transferred to also satisfy the octet rule. Octet rule, it means they should have 8. To determine the number of valence electron in an atom, look at the main group here. I've explained you, I've shown you the partial periodic table. Looking at the group number on the periodic table, you should be able to determine the valence electron. For main group, the group number equals to the valence electron. For transition metal, all have 2 valence electrons. Why? All right. Why do they have 2 valence electrons? Because of the 4s and the 3d. The ISN value is 4s with the 2 electrons. You can check that for the transition. Now, Lewis structures for atoms is just representing the dots, using the dots to represent valence electrons. So here, these are valence electrons. It's not only limited to oxygen. Oxygen is in group 6, so you have to put the 6 dots around it. If you count out this, they are singly distributed fast before you start pairing them up. So this predominantly will form 2 bonds based on the unshared pair here. See that there's 2 dots. This is just illustration on how to write the dot symbol for element. Lithium is in group 1 dot, beryllium is in group 2 dots. You don't pair them up. Boron is in group 3 3 dots around it. Group 4 is in the middle of getting to 8. So it has 4 dots around it. Then nitrogen, 3 dots, and all any other 5A will assume the same configuration. It also applies to oxygen and fluorine, and even neon. They are all paired up in group 8, except for helium, which does not have 8 dots around it. This is pretty straightforward. I know you covered in Introduction to Chemistry. Please make sure you make your own notes on this one as well. So we asked ourselves earlier on, why do chemical bonds form? Lewis bonding theory explains that because bonding results in a more stable electron configuration. More stable means lower potential energy. So chemical bonds are formed by atoms either losing or transferring, sharing of electrons. Usually it's result in all obtaining all other shared with 8, and that is the octet rule. You should be able to state the octet rule, even though there are some exceptions, which we look at it later on. When atoms react to form compounds, they either lose and end up with 8, or gain and end up with group 8 element. This is what we call the octet rule. Octet rule. Here is an example on the Lewis dot symbol for element silicon. How do you know, or how do you write the dot symbol for silicon? First of all, you have to ask yourself which group is the element in question. Right, look at this. Silicon is in group 6 by looking at the periodic table. Let me just make sure that I'm saying or passing the correct information. Silicon is Si, silicon S, not Si, but S. This is the chemical symbol for silicon, S, group 6A. If you look at 1s2, is 6. So silicon has is in group 6, and it has 6 valence electrons, 6 valence electrons. So if I write that for group 6A, this will be Si1, 3, 4, 5, 6. So for 6, they'll have 6 valence electrons, 6 valence electrons. Now, the learning question here is another follow-up question. Are these Lewis symbol for chlorine? Chlorine is in group 7. So here, group 7. It has 7 valence electrons. So we need to have 1, 2, 3, 4, 5, 6, 7. That's how you write the dot symbol for chlorine. And if you look at the position of the single electron, doesn't really matter where you put. The correct answer for this is no. The first two are different structures, Lewis structures, because of the different placement of electron. No, so they do not represent the Lewis symbol for chlorine. Need to know that. Now, they are another learning check question. They are dash pair, paired and dash unpaired electrons in Lewis dot symbol for fluorine. So it should be for fluorine. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, there's 6. They are dash paired and dash unpaired. So it should be 1. There are 6 paired. So it's C. 1, 2, 3. There are 6. Then pair. Please look at problem number 37, 38 on page 438 and 439 in the text. It will give you good practice before you take the quiz or exam. Now, let's move on to 10.4, 10.4 ionic bonding Lewis symbols and the lattice energy. Okay. First of all, what is lattice energy? Lattice energy is the amount of energy required to break apart or dissociate 1 mole of a compound, right? It's the amount of energy required to break the ionic bond we call the we call the lattice energy or lattice energy. Lewis symbol can be used to represent the transfer of electron. If you look at the reaction between potassium and chlorine, an electron is transferred from potassium to chlorine, and what result is the ionic compound. And please use the parentheses to indicate which atom actually has excess electron, which one has less number of electrons. If I look at the cation, this has 8 electrons, this has 8 electrons. Remember what we talked about earlier on, that atoms tend to form stable compounds with a low potential energy. So this is cation with 8 electrons valence. This one also has 8. It achieves the octet rule we talked about. Please look at problem number 404142 on page 439 on how to write the ionic compound with the charges and showing the transfer of electrons. So here is the electron configuration. I know we covered in the previous chapter the electron configuration of neutral atoms and electron configuration for ions. This has no electron, the 4s sublevel, because it's lost ISN value, leaving us with K positive, K positive. This is just what Lewis predict, and for ionic compound, the number of electron transferred or lost metal to a non-metal should gain in order to attain a stable electron configuration. This is the octet rule. Lewis also model also allow us to predict the formulas for ionic compounds. In the exam, I may ask you to predict the ionic formula for the compound between this element in this group and this element in this group. You should be able to use the Lewis model or any other general understanding. Lewis model also allows us to predict the relative strength of resulting ionic compounds. This is from the Coulomb's law, ionic bonding and the lattice energy. What is the lattice energy? Remember what I said earlier on, lattice energy is the amount of energy required to break 1 mole of, let's say, sodium chloride into constituent ions. The outset, the crystal lattice is the alternating cations and the anions from the gaseous atoms coming together in a crystalline form. Yes, there is an alternating positive. We just show you that this is an ion and a chlorine. There is alternating sodium, chlorine, sodium, chlorine. All right, and the crystal lattice is held together by electrostatic attraction of cation and anion, positive, negative, positive, negative. So lattice energy here is the energy released when ions come together. You see the ions are coming together when they form, they release the energy. You see energy is being released there, that matter. So the extra stability that accompanies the formation of crystal lattice is measured by the lattice energy. Lattice energy should be able to define, by the way, lattice energy is the energy necessary or what is required when a solid crystal forms from separate ion in gaseous state. It's highly isothermic, that means it gives away heat. It's hard to measure. The point here is this one is hard to measure, but we use what we call Born-Haber cycle, which is the same as Hess's law of heat summation. We will use the same approach to calculate the lattice energy. Lattice energy also depends directly on the size of charges and inversely proportional to the distance between the ions. I want to emphasize here the size of the charge. Ni, for example, compared to Ca2 positive. Yes, shall I minimize this for you to see? Cation, this has larger positive charge, whereas sodium has the least based on the charge on that. As I said, Born-Haber cycle, this is the same as, the approach is the same as the Lewis, not Lewis, but Hess's law of heat summation. It's just an hypothetical series of reactions that represent the formation of ionic compound. We'll be looking at an example on how Born-Haber cycle is used to calculate the lattice energy. We need to understand, first of all, how the whole process works. Remember what we say about Hess's law, you have to find the summation for the overall enthalpy of reaction. It's the summation of individuals. So in this case, we have salt, which is sodium, needs to form the metal ions under the metal ions. You need also to factor in the ionization energy. Here is an example on how Born-Haber cycle is used to determine the lattice energy. At the outset, this is what we know. We know that in order to form 1 mole of sodium chloride from our chlorine atom and sodium atom, this is what it takes, is what we need. And in this case, you know the overall, but in between these steps, you need to find the lattice energy. It's just a question of rearranging the equation in order to remain with lattice energy on the left side, everything right side. And please check the physical state as well. Physical state as well. Remember, it's product. Here is the product. Instead of adding product, you subtract, even though it is still negative. It's still negative. It's just a summary of the previous steps. In diagram, please make sure you read the relevant section in the text. Practice on how to use the Born-Haber cycle to determine the lattice energy. You should be able to state a trend on the periodic table. This is trend of what? Trend in lattice energy. You need to know that. Just like the atomic radius, ionization energy, the trend on the periodic table, the force of attraction between the charged particle is inverse proportional to the distance between them. Larger ions means center of positive charge nucleus, cation is far away from the nucleus. So you need to remember that. If you look at the trend here on the lattice energy, all these are group 1. The anion, the negatively charged, does not change, and it is in line with the amount of energy we need to break in 1 mole. All right, so remember 1 mole, as you go down, the atomic radius increases, and therefore it will be much easier to determine which one will be appropriate for you. So please note the trend as you go across the periodic table. Remember the charge override, even though you see here that they are almost the same distance, right? This one will have high electrostatic force of attraction based on the ionic charge, please look at the problem for the 344, 45 on page 449 on the trend on lattice energy. Should be able to make your arrow notes as well. We just looked at how to use the Born-Haber cycle. It's just like multi-step approach in determining the lattice energy. I will not expect you to memorize the table you see on here. It's just illustration on what's going on for group 1 or, the same ion. You see here, there anion is changing as you go down. And I'm not surprised why why you look at this sodium, this means it's increasing down. and it's getting weaker and weaker. You need to know how to read the table here. On the side of increasing charge on the cation, so the charge first of all overrides the size. All right, override the size here. Increasing cation, yes. Increasing cation because of lithium, sodium, it keeps on increasing, except like for rubidium chloride, almost 670, almost 670, right? Almost 670. Let's see which one of the following, all right? The following is wrong according to, so if I look at rubidium, decreasing magnitude. So you have to have rubidium for that in order to determine the order in which they're increasing. Just wanted to check my notes. Make sure we are all on the same page. How will you know which one is which? We have to place the following in order of decreasing in magnitude of lattice energy, decreasing. So we need the strongest. So if I look at sodium, this is the smallest and it's gonna be hard. This means greater. This means the least among the four because of the size of the cation. You know, this is the smallest size, followed by potassium, followed by rubidium. To explain why you follow this pattern B, the correct answer is B for the learning check on Blackboard. Learning check on Blackboard. Again, like previous section, ionic bonding model versus reality. This is where the Lewis will predict that ionic compound have the highest melting point and boiling point. Please read on ionic solids. Electrostatic attraction is non-directional, unlike in covalent, it's directional. Therefore, there is no ionic molecule, but just exists as formula units or just the formula. You don't use molecules for non-metal, So Lewis bonding also versus reality. Lewis theory implies that the attraction between ions are strong. Lewis is strong. Lewis theory predicts and the compound should have high melting point. Yes, so reason for that is there is transfer of electrons, which when that happens, cation and ions are attracted to one another, and the compounds have high melting point. This is what we already know. So properties of any compound, you should know hard, brittle because when you, why is it that any compound are brittle? It's because if we have sodium positive, chlorine, what happened here is alternating positive and negative. If you align a negative, positive and positive, and and they are just touching one another, positive and positive to repel, and this explains why, you know, we ionic compound are so brittle, because positive and positive, when they come in contact, they shatter, they repel. That explains why they are brittle. Common example on properties of ionic compound is using sodium chloride. Regular pattern agreed, but if we put in salt heat, you'll see that they lose this pattern and they start just disintegrating. Please read on ionic bonding model versus reality. I know you can make use of that. Other than that, I just want to wrap up section 10, part A, All right, this is something we learned earlier on, properties of ionic compound. They are strong electrolytes, conduct electricity when dissolved in H2O. While still in H2O, see, it doesn't conduct electricity. This one conduct electricity. That marks the end of part A. We will come back again in part B.